Most people build models and make forecasts off a single summary and then watch those decisions fail in the real world. The gap is simple. They think one number can tell the story of how two variables move together. Mathematically, that compresses a whole two-dimensional pattern into a scalar, which erases shape, outliers, subgroups, and changes in variability. Picture yourself presenting a tidy average effect to a team, quietly unaware that the actual relationship would have been obvious and contradictory if you had just looked at the points on a plane. A scatter plot is the antidote to that compression. One axis carries one variable, the other axis carries the second variable, and each case becomes a dot whose position encodes both values at once. This is not decoration. It is the geometry of your data. If you only read a number, you see at most one shadow of the situation. When you read a scatter plot, you read the shape of dependence, and you get to see where that shape breaks. Consider advertising spend and daily sales for a small store. You could compute an average revenue per ad dollar and stop there, but that would be the same mistake that keeps budgets stuck. And if you instead chart each day as a point, with spend on the horizontal axis and sales on the vertical, you start to notice what actually happens when the store ran $100 in ads versus when it ran very little. Some days sit far above a simple line, some days below, and the pattern across days tells you what a single average could never say. The first thing a scatter plot shows is direction and form. Is the cloud tilting upward, downward, or neither? Is it shaped like a rough line, or does it bend like a curve? That shape is the kind of relationship that could exist between the variables. An upward tilt hints at positive association, a downward tilt at negative association, and a diffuse circle hints at no meaningful association. No single number can show you these possibilities in one glance. The most common beginner mistake is trusting a correlation coefficient or an average difference in isolation. People compute it, declare victory, and then move on to fitting a simple line as if nature promised to be linear and well-behaved. Without the picture, they assume that residuals are small and evenly spread, that no oddballs exist, and that any change in one variable means a fixed and predictable change in the other. That is not care. That is wishful thinking hidden behind a statistic. The cost is real. You will fit the wrong shape and predict badly. You will miss obvious clusters that should be modeled separately. You will let outliers steer your estimate and make your effect look bigger or smaller than it is. You will assume variability is constant when it swells with the level of the predictor. And when the model gets deployed, you will spend money and time correcting the behavior of systems that were built on a fragile summary. There's a simple correction. Plot the data first, always. Label your axes clearly with variables and units, and use small points so dense areas can be seen. Then check for 4 things in order: direction, form, strength, and outliers. Write down what you see in plain language before you compute anything. That habit prevents a long list of errors. Direction means whether increases in the horizontal variable tend to pair with increases or decreases in the vertical. A clear upward trend across the cloud suggests that higher levels of the predictor tend to accompany higher responses. A downward tilt suggests the opposite. A blob with no tilt suggests that learning from one variable to predict the other will be weak. If your plot has vertical stacks because many points share the same horizontal value, note that too. It affects interpretation. Form is about shape. A straight line pattern says a linear summary could work, while a bend says it will not. With our advertising and sales, you might see a curve that rises quickly at low spend and then flattens, a classic sign of diminishing returns. You might even observe that when you spend about twice as much, sales increase, but by less than twice, another hint that a simple linear formula would overpromise at higher levels. The sign of the tilt and the presence of a bend matter more than any computed coefficient at this stage. Strength is about how tight the cloud is around the trend. If the points huddle near a notional line, or a curve, the association is strong. If the points are widely scattered, the association is weak, even if the direction is clear. Strength matters because it forecasts how much error you should expect when you predict. Beware of overplotting when you have many cases. Dense areas can hide structure. Techniques like transparency or a small amount of intentional jitter help reveal density without faking patterns. Outliers deserve their own look. A single day that went viral can sit far above the rest and distort your sense of the relationship. If sales jump to 5 times the usual level on a day with ordinary ad spend, a naive summary will overstate the average effect, and a correlation will inflate. In the picture, that point is obvious, and you can decide whether it belongs to the same data-generating process or should be treated separately. Without the picture, you would never know you were being misled. Clusters and subgroups are invisible to a single number, but they stare at you from a scatter plot. Maybe you have data from 2 marketing channels, or 2 regions, or weekends versus weekdays. Each subgroup can have its own tilt and tightness, even if the overall cloud looks noisy. If you color or mark points by group, the structure jumps out. The fix is not a fancier statistic, it is stratifying your thinking and your model to match the real sources of variation. Changing spread across the range is another pattern this scatter plot exposes. Often the cloud looks like a funnel, narrow at low values and wide at high values, which means the variability of the response grows with the predictor. That violates assumptions behind many simple models, and it warns you that a uniform error bar would lie. You can respond by transforming variables, by modeling the changing variance directly, or by using robust approaches that do not let widespread at one end dominate the fit. None of those steps would be motivated by a single number. Small samples bring their own trap. With only 10 points, almost any orientation can look plausible if you squint, and random scatter can look like a faint line where none exists. In that setting, a correlation estimate swings wildly, and a confident story drawn from it is fiction. The plot does not remove uncertainty, but it makes the uncertainty honest. If the shape is not clear, the answer is not to compute harder. It is to get more data or to temper your claims. Axes and scaling matter more than most people think. A steep trend can look flat if one axis is stretched, and a gentle trend can look dramatic if the scale is cramped. Keep units consistent and scales comparable, or annotate when that is impossible. If you truncate axes, be explicit about it, because a zero baseline can change how you perceive relative change. The geometry should reflect the truth of the measurement, not an accident of plotting defaults. Conditioning on a category can completely change what you see. Color the points by channel, and you might notice 2 clusters, each with its own steady upward tilt, while the combined data look flat. That is a version of Simpson-style reversal. The overall pattern hides the subgroup patterns because the groups occupy different parts of the plane. When you see this, you do not average effects across groups. You respect the strata in your analysis. Again, the plot makes this visible before any computation. A scatter plot does not grant you causality. It shows association and sometimes direction over time if you add arrows or animate points across days, but it cannot tell you what would have happened otherwise. Time order matters, feedback loops matter, and lurking variables matter. Seeing a clear association should trigger questions about mechanisms and controls, not declarations about cause. Use the plot to design better tests, not to pretend you have already run them. Now compare this with what a single number gives you. A correlation coefficient collapses direction and strength into one value under the assumption of a linear form and constant spread. It cannot see curvature. It cannot tell you if a few points are doing all the work, and it cannot reveal separate groups that deserve separate models. Even when you plan to report that number later, looking at the plot first tells you whether the coefficient will be reliable, fragile, or meaningless. Range restriction is a classic failure mode that a scatter plot exposes, but a number conceals. If you only look at job applicants with top test scores, the horizontal spread shrinks, and any genuine association with performance seems to vanish. A correlation calculated on that thin slice will be small, not because there is no relationship, but because you cut off the variation that reveals it. A quick look at a wider scatter that includes scores above 90 and below, it would show you the danger immediately. Numbers alone will not warn you that you are zoomed in too far. Here's a practical routine you can use. When given paired data, sketch the scatter plot before running any summaries. Check direction, form, strength, and outliers, and note any subgroups or changing spread. Decide whether a straight line captures the main trend, or whether you need a curve, a transformation, or a piecewise approach. Only then compute the correlation, and later fit regression, and only interpret those numbers in the light of the shape you saw. The essential shift is this. Stop asking what a single number says, and start asking what the shape of the relationship looks like. Treat paired data as geometry plus variation, not as an arithmetic problem waiting for a summary. Once you see the cloud as information rather than noise, you make fewer assumptions, catch the traps early, and your statistical story starts from what is actually there, not from what you hope is true. Next, we pin down the correlation coefficient, what R actually measures, so that when you do compress a picture into a number, you know exactly what was kept and what was lost.